I'm just nosy. I like people. I'm a people person, so I like to hear and natter on. Right, we are going to start our last section. Hopefully we'll get it finished. I think we should. A lot of what you're going to do is the same thing that you've always done. You're going to do product rule and quotient rule. The main difference is that we are going to introduce trig functions. From 142, which hopefully isn't too far away in your history, there are 6 trig ratios. You recognize them? Every single one of them has a derivative. And here they go. The derivative of sine x is cosine x. So you might want to have a version of this little table on a cheat card somewhere so that when you're doing questions, you'll be able to remember them. The derivative of a cosine is negative sine x. The derivative of a tangent is secant squared x. The derivative of a cosecant is negative cosecant x cotangent x. The derivative of a secant is secant x tan x. And the derivative of cotangent x is negative cosecant squared x. And I'm just telling you that that's what they're equal to. So if you have to differentiate a tan, the answer will be secant squared x. If you have to differentiate a sine x, the answer is going to be cosine x. Fair enough? Now, I can prove, if I had plenty of time, I can prove a couple of these guys by using those two. In fact, I can prove all 4 of these, so it's more than a couple, by using these 2. But these 2 I can't really prove to you unless you do some advanced math. But I can try and kind of prove it to you. So I'm going to prove to you that, or sort of prove that the derivative of sine x is cosine x. And I'm going to do it visually. Now, can you imagine that I'm good at drawing? Which I'm not. Actually, for me, not bad. Would you agree that's a fair representation of what the sine function looks like? Great. Not great, but you get the gist of it. And here's our y-axis. Here's our x-axis. And I'm now going to sketch its derivative. And we have done this process before. So in the case of this, it's going to be find the places where they're the tops of hills and the bottoms of valleys, right? So there are about quite a few of them. And you drop an invisible dotted line that really isn't there, and you rub them out when you're finished, if they are noticeable. And this breaks my shape into 1, 2, 3, 4, right now 5 different regions. And at the point where the bottom of the hill is, the tangent line is horizontal, which makes it 0. And it makes it 0 here, it makes it 0 here, and it makes it 0 here. Do you remember doing this process for polynomials? Now, in each of these regions, what I now do is I find out, is it positive or is it negative? So in region 1, would you agree that all the tangent lines are pointing downwards from left to right, which means it's negative? And then in region 2, they're all pointing uphill. In region 3, they're all downhill. In region 4, they're all uphill, and whatever you can see of this one. What I'm now going to do is start in this region and go through all these points. Now, if I start in this region, it goes up, and it comes down, and it comes down, and then it goes up, and it goes up, and then it goes down. What does that look like to you?
Cosine.
Have I kind of sort of proved to you that the derivative is cosine? Right? And if I haven't, can we fall back on, trust me, I'm a mathematician. If I tell you it is, it is. Okay? That may be a backup plan. And moving on then, let's show you the types of things that you're going to be differentiating. And also I'll be introducing in some of the later questions, the third rule of style points. Rule number 1, make me look like an original. Rule number 2, factor the heck out of it. And sometimes, this is a sometimes, rule number 3, use trig identities to make it look pretty, right? So we're getting, in some questions at least, we will be using that. There is a rule when trig functions are involved that you should try and write your derivative without using fractions. That's just a convention. So, you know, your answer could be sine x over cosine x, but we don't want you to write it that way, right? We want you to write it as without being a fraction, if at all possible. So let's start with a really, hopefully straightforward question. Suppose I wanted to differentiate this function here. Well, the derivative of a sine is a cosine, so 3 sines get you 3 cosines. Does that sound reasonable? And the derivative of -2 cosines gets you, oh, wait a minute, -2 times something that's negative, that turns into a +2 sine x, and the derivative of x squared is still 2x. Are you comfortable about where each of those pieces came from? Right? This guy over here is what I was using. Are we good? Let me do tangent. I'm telling you the answer, but let me show you how I can prove it. I'm going to use a trig identity that I hope you remember, and that is a tangent is a sine over a cosine. You remember that property that tangents are sines divided by cosines. And so I can now do, which rule from yesterday do you use to differentiate fractions?
The quotient rule.
Okay, and in the quotient rule, we call the top guy f, right? And we call the bottom guy g. So this is going to be f dash g, take away f of g dashed over g squared. This question is good because it's going to show you the style points that get used with trig, right? Which is use identities to make it as nice as possible. So if you differentiate sine, you get a cosine. If you leave the g alone, you get times another cosine. Take away, you leave the top alone, you get sine x. And if you differentiate a cosine, you get negative sine x. And the whole thing is over cosine squared. Now, when you take cosines times cosines, right, and you get a thing called cosine squared, right? That's what we've got here. We write that, and I'm sure you've seen it. Don't you write it like that? That's the convention. That's kind of an ugly version of cos squared. Now, what happens when you multiply a negative sine x with another negative sine x? You get plus sine squared x. And on the bottom, I'll call that cos squared x. Now, it's a nice answer, but it could be made nicer. Is there any trig identity that you can remember that tells you what cos squared plus sine squared? You probably had it as sine squared plus cos squared, which is the same thing. What's that equal to?
Equal 1.
Is equal to 1. And so you've now got 1 over cos squared x, which is much nicer, right? So style points is doing its job. Now, when you look over here, do you see the answer isn't written as 1 over cos squared? Because the convention is, if it's at all possible, don't write a fraction. So I'm going to use this identity. Isn't the secant of x the same thing as 1 over cosine x? Remember that? A secant is 1 over cosine. So isn't that basically 1 over cosine squared becomes a secant squared? And that is the proof that the derivative of a tan is secant squared. So is this list becoming less magic and more, yeah, I could understand why the answers are the way they are. You could do if you've got time the other three, but we don't. So we are going to move on and try something a little bit sneakier. Let's suppose I want to do sin x times cosine x. So I want the derivative of sin x times cosine x. Are we all comfortable that that's a product rule this time? Great. So you're going to do trig functions with product rules, trig functions with quotient rules, and if you're really lucky, things like 3 sin x, where you can basically just write the answer down. So the derivative is going to be f dash g plus f of g dashed. If you differentiate a sine, you get a cosine times another cosine plus a sine times the derivative of a cosine is negative sine. And now you're going to be left with cos squared x, take away sine squared x. No, that's not 1. I wish it was. If it was cos squared plus sine squared, it's 1. That is equal to something. It's equal to a double angle. Does anybody know, remember, what cos squared take away sine squared is? Cos squared take away sine squared. Last chance. Cosine of 2x. So maybe I should write them down here as we use them. We've already used that sine squared plus cos squared is 1, right? And I'm now telling you that cos squared x take away sine squared x is the cosine of 2x. Does anybody remember what 2 sin x cosine x is?
Sine 2x.
Well done. You nailed it. Yep. What else have we used? Oh, we've used the fact that tan x was sin x over cosine x. Wasn't one of the things about trig the number of identities, relationships that make something in trig turn into something nicer? Like that one's a really nice one, but there are other examples, right, where you could use it. So let's put in some secants and cosecants. Okay. Suppose I have a function 2 times secant theta plus theta cotangent theta. And I want to find its derivative. Well, 2 times secant theta, a secant gets me a secant tan. So the derivative of this guy is just 2 times secant theta tan theta. Done. How am I going to do this one? Theta cotangent, what method? Theta cotangent. Theta times cotangent. Product rule, quotient rule.
Product rule.
There we go. So it's going to be what? F dash G plus F of G dashed. In this case, kind of like that answer, so it's cool. 1 times the cotangent of theta plus theta times the derivative of a cotangent is negative cosecant squared. And so I have 2 secant theta tan thetas plus a cotangent of theta, take away a theta cosecant squared theta. And the good news here is there isn't really anything going on there that you can do any trig identity to. It's ugly and it's going to stay ugly. And now I got a chance to get one of my many grumps over with. What's that symbol called? Not a trick question. What's it called?
Theta.
This is what I hear. Theta, right? This is what it is. Do you notice I call it theta? When I say theta, are you hearing theta? How can Americans screw up a totally different country's alphabet and pronounce it wrong? How did you manage to do that? Did you just
call it Z?
Well, I hope you call it Z.
No, it's Z.
Well, I want to give you a surprise, Nick. It might shock you to know this, but it was my alphabet before it was yours, and I'm right and you're wrong. And it's theta, not theta. It's a masculine sound. It's theta, right? It's not theta. That's kind of feminine sound, right? Theta. So we all got to practice that. And Nick, you practice Z. Because if you go to Britain, people will laugh at you. They'll think that foreigner can't speak properly. Oh, this job's so much fun. I get to insult students and get paid at the same time. It's not a bad job, is it?
Well, wasn't it Greek before it was Scottish?
It was. You're quite right. I bet you if we got someone who's Greek here, they would say, that's not how you say that. And they'll have a different way of emphasizing the vowels, in which case we'll both be wrong. But Z, I'm claiming, right? Because that is our letter of the alphabet, right? And so we're good. I'm just scanning through to see what we can find. Let's see what we get there. This is a version of question 6. F of theta is sine theta over theta take away cosine theta. So hopefully you'll all say, yep, product rule. So you want to find its derivative. Do f dashed g plus f of g dashed. And this guy, when you differentiate him, is a cosine, and you leave the other guy alone. And then you leave the first fella alone, and you differentiate this. Well, that's just like differentiating x, you get 1. And differentiating a cosine gets you a negative sign. So differentiating a negative cosine gets you a plus. 2 negatives make a plus. And now I'll distribute. Theta times cosine of theta, take away cos squared theta, plus a sine theta, plus a sine squared theta. Are we good with this one? Now, I'm going to try and trick you. And the fact that I'm telling you I'm going to try and trick you should help you not be tricked. Can you simplify that expression?
The sine squared and the cosine squared equal 1, right?
Ah, do they?
No.
I almost caught you, but you changed your mind, right, Alison?
Yep.
The reason I did that is because a lot of times, and it's very easy to do, isn't that almost so easy to skip over? Couldn't you just say +1 because you want something to be nice?
Yep.
Now, it looks kind of like this guy, doesn't it? But isn't it the wrong way around? So as far as the textbook is concerned, and as far as WebAssign is concerned, that's as simple as that answer is going to get, which means it really didn't get simple at all. Agreed what you started with is what you ended up with. So there's no guarantees. This is, I guess, the moral of this story. There is no guarantee that you're going to get an answer that could be simplified, right? Once you've differentiated it, it might be really ugly looking and it stays ugly looking. Right? Let's try this one. This is 8. Now, put a little bracket just for emphasis here. This guy is cos squared t. And if you leave it written like that, you won't really be able to figure out how to differentiate. You can't say, oh, I'll just do a power rule. Isn't the power rule for t squared? It's not for cos t squared or e to the t squared or anybody else squared. Isn't the power rule only for t squared, right? So write that, carve it out your brain, never do it. But I can write this in a way that is going to allow me to do the product or the quotient rule on it. So in this case, it's pretty clearly a product rule. How should I rewrite cos squared t?
Cosine t times cosine t.
Does that make sense? So if someone asks you to differentiate tan squared or cotangent squared, aren't you going to split it into the same guy times himself and use a product rule on it? That's essentially what you're going to do. So this is going to be an f and this is going to be a g. So the derivative using the product rule is f dash g plus f of g dashed. And if you differentiate a cosine, you get a negative sign. And then you leave the second guy alone. Plus, you leave the first one alone. And you differentiate a cosine, and you get a negative sign. And to save room, because I'm running short, you end up with negative 2 sine t cosine t. That guy can simplify. Somebody over here is going to make that nicer. Okay, I may have to adapt it a little bit, but it's still going to work. This guy, somebody over here. I'm waiting for a volunteer.
There's been negative sine 2x.
And in this case, you're right. In this case, t's, but you were right.
Oh, I'm sorry. Yeah.
Yeah, I know what you meant. Are we cool with that? So didn't we get a style point? We made it nicer. Okay, let's do a quotient rule one because I seem to be focusing on an awful lot of product rules. And it didn't take me long to find one. It's question 10. Well, this question doesn't need anything to be done to it. It's ready to go. And would you agree it's got that classic fraction thing that means it's going to be the quotient rule? So that's f dash g, take away f of g dashed, all over g squared. You differentiate the top, you get cosine theta, leave the bottom alone, 1 plus cosine theta. Take away, leave the top alone, sine theta. And if you differentiate 1, you get nothing. If you differentiate that guy, you get negative sine theta, all over the bottom squared. So far, so good? Okay, what do you think I'm going to do next? Because remember, style points is kicking in there. What do I do next?
Do you distribute the top?
Okay, so cosine theta plus cos squared theta. 2 negatives make a plus, so plus sine squared theta. 1 plus cosine theta squared. Okay, keep the style points going. Anything you can do on the top that looks a little prettier.
Sine squared plus cosine squared is 1. 1 plus cosine squared over 1 plus cosine quantity squared.
Gotcha. I wish I had actually written 1 plus cosine theta on the top. It might help my next question. That could be the end, right? That could be, yeah, we done pretty good, but you can do better. I see a little cancel movement. Isn't 1 plus cosine theta? Isn't that 1 plus cosine? So can't you take one of these and cancel it out with one of these? And your final answer, sounds like a quiz show, my final answer is that. Are you comfortable with that? If you're not, this is what I'm doing. I'm calling this 1 plus cosine theta, and I'm putting a bracket around it. And I've got a 1 plus cosine theta on the bottom, squared. And can't you cancel one of these for one of these and leave yourself with that? Does that help?
How did the like the cosine theta plus cosine squared theta plus sine squared theta turn into the cosine theta plus 1?
Cos squared plus sine squared is 1. Right, one of the identities. It's the same thing as sine squared plus cos squared, right? Doesn't matter which way around you write it. And sine squared plus cos squared is 1. So I'm using a trig identity. So a cosine on its own plus these two guys that give me 1. So cosine plus 1. Looking good? Yeah, see a nod? I like nods. Would you agree there's not an awful lot different here, except we're doing it to trig things, right? We're still doing product rules and quotient rules. The thing that is kind of maybe different is, isn't it the style points at the end, where you try and make it look pretty? That will come to you because you'll be doing hopefully enough of them to be good at it. Don't like that one, it's pretty ugly. Oh, this one might look nice. The ones that I just skipped, the answer is either a product rule or a quotient rule. The reason I kind of skipped them is that there wasn't any style points. So when you were finished, you had this big ugly fraction that you couldn't do anything to. And that was the answer. I much prefer ones that have style points in them. So this is F and this is G. So the derivative is F dash G, take away F of G dashed all over G squared. Now, if you differentiate the top, that gets you nothing, and the derivative of a secant is a secant tan. So you're going to get secant tan. And then you multiply it by the untouched bottom. Take away the untouched top, which is that guy, times the derivative of the bottom. And the secant gets me, I don't have enough room, so I'll have to squeeze it in here. Secant tan. So this guy times him, take away this guy times him. I'm going to distribute. Secant tan times 1 gets me secant tan. And secant tan times that gets me negative secant squared W tangent. This guy times this guy gets me take away secant W tan. And this guy times this guy, I get take away secant squared W tan W. I need to write smaller or start further to the left, all over this guy squared. Okay, I'm looking around here to see if anything kills off anything else. Do you see anything in the top that might be killed off by something else also in the top? I've got a secant tan, take away a secant squared tan, take away a secant tan, take away a secant squared tan. Right, that's 4 terms. any of those combine nicely? Okay, I'll phrase it a different way. They do combine nicely. Tell me what they combine to then.
The secant times tans cancel out, and the secant squared times tan. That's going to be -2 secant squared W.
That's it. You can think of them as X's and Y's if it helps. Yeah, secants and tans and whatever they happen to be. Think of them as X's and Y's. Now, in this particular case, that's good as it's going to get. So you're finished. Let's do a triple product rule. Yesterday, I think it was Nick, it might have been someone else. We looked at how to do a product rule when 3 things were being multiplied together. What? I think it was you. Was it you, Nick, that did it?
It did what? Yesterday? Yeah, that was me.
Ah, okay. So you want to just state it again so the others can catch up with it. What's the product rule based on
Well,
this?
You do the one derivative or derivative one at a time. So derivative f times, yeah.
Okay. What would the second one be?
Yeah. Then you do it again for g, where it's f times the first derivative of g times h, and you do it again for f first derivative plus times gh.
Or any combination thereof, right?
Yeah, doesn't matter.
So what we have here is leave that alone, differentiate him, which is actually kind of boring because nothing actually changed. Leave this guy alone, differentiate him, leave that guy alone, in which case you get theta cosine of theta e to theta. And the last one is differentiate him and leave these two alone. And so you get sine theta e to the theta. In this case, the only style points that I can really see of any use is to pull out an e to the theta. So you have that guy plus that guy plus that guy. And that's into that one. And by the way, this is not quite the same thing, but it's like 14. So let's find equations of tangent lines now. When you start off with,
Oh,
yes.
I have a quick question.
Sure.
Okay, so I noticed that when you differentiated theta, you turned it into a 1.
Correct.
Okay, so it's not considered a constant that would turn into a 0.
No, 5 would be a constant. Theta is like an x. If you said x times sine x times e to the x, wouldn't that be essentially the same question? If I said to you differentiate x, you would say 1. So I think it's just the fact that we're not using theta so much that it kind of threw you a little bit. But it is,
Okay.
It is a variable and you've got one of them. So when you differentiate, you got 1.
Okay, thank you.
Let's find the equation of a tangent line. So number 15, we have y equals sine x plus cosine x. And the point that we've defined the tangent line, equation of the tangent line is at 0, 1. Well, if you differentiate, you get cosine x. Differentiate a cosine, you get negative sine x. If you want the slope of the tangent line, don't you evaluate this at, in this case, 0. So it's a cosine of 0, take away the sine of 0. And the slope of the tangent line is 1. to get the equation of a tangent line, just like in the other times that we did it, we use this fella. And so it's going to be y take away 1 is 1, x take away 0. And adding 1 to both sides. Done. So a nice simple one just to get us into the swing of things. So you want to find the equation of a tangent line, differentiate the function, plug in the x coordinate of p, and the number that comes out is the slope of the tangent line. You then use what's called the point slope equation, which is this guy, plug in the y coordinate of p, plug in the x coordinate of p, plug in the slope that you've already found, and then kind of make it pretty, and you've got it. Now, if I had time, couldn't I have plugged this guy into Desmos, and couldn't I plug this guy into Desmos, and you'd have a guy in a little nice tangent line. Isn't that the kind of picture you'd see, and you'd know you'd done it right? Because isn't that the tangent line? So let's do one with more awkward values. So y is 16x, the sine of x. And we're being asked to find the equation of the tangent line at 1/2 pi, 8 pi. Call this f, the whole package. Call this bit g. So it's a product rule question. Differentiate, you get 16, leave the other guy alone. Leave the first guy alone, that's f, and multiply by the derivative of sine, which is cosine x. I'm now going to find the derivative at pi upon 2. So that's what m is. 16 times the sine of pi upon 2 plus 16 times pi upon 2 times the cosine of pi upon 2. And this is from your 142 world. What is the exact value for the sine of pi upon 2? What number is it? Pi upon 2, the sine of.
1.
Nailed it?
Is it square root 2/2? Oh, no.
Oh, no, but that guy that you just mentioned is pi upon 4. So that is an answer for a different angle. So you weren't that far away. But for pi upon 2, it's 1. And this guy here is 16 times pi upon 2 times, and what's the cosine of pi upon 2? It's a number as well, of course. Cosine of pi upon 2.
0.
0.
So guess what? The slope of the tangent line is 6. Now the equation of the tangent line uses the point slope equation. That's going to be take away 8 pi, it's this guy. 16, x take away that guy. I get 16x, 16 times 1/2 gets me negative 8 pi. If I add 8 pi to both sides, that is a very pretty answer. It's just a straight line that passes through the origin, y equals 16x.
You said the sine of pi over 2 is 1,
Correct,
and the cosine of pi over 2 is 0.
correct. I mean, if I draw little pictures of them, that's what the sine looks like. And there's pi upon 2. And that height there is 1. If you did a cosine function, it would look something like this. And here is pi upon 2, and you can see it's 0. Right, I don't have enough time to do another full question, but we pretty much covered everything that you need to know. So I'm now going to hit you with these guys. You can imagine questions where you need to find the sine, the cosine, or the tangent at a particular number because you're going to get, you know, the slope of a tangent line. So who's got a good memory? Who knows their unit circles? Sine of pi upon 4, Vanessa. I know you know that one.
Oh no, I wasn't good at memorizing the unit.
But you actually, I think it was you anyway, who went and accidentally gave me the right answer for a different question.
Unfortunately, that wasn't
that was
me.
me.
I wish.
Oh, okay, who was it that said that?
Is square root 2
Uh-huh.
over 2.
Yeah.
And
That's
2 over square root 2. Yeah.
Right, so it's that one. What's the cosine of pi upon 3? Well, let's do it a different way. I'm going to just write down what are called the standard angles. That's the angles from 0 to 90 degrees. But I'm doing them in radians because that's what we do. We do these guys in radians. So when you are dealing with trig functions in calculus, it's just radians. Just that's what it is. So I'm going to do just the sine, the cosine, and the tangent. Now, if you need to know the secant, don't you just turn the cosine upside down? If you want to know the cosecant, you turn this answer, you know, reciprocal upside down and cotangent. So pi upon 6. What is the sine of pi upon 6? Anybody? Pi upon 6.
Is it root 3 over 2? Oh,
Okay.
that's a guess. Oh,
Oh, it's the right number. It might not be for this one, but it will be for one of them. So let's show you. I'm going to go to my calculator and make sure that I'm in radians, which I am. And I'm now going to do the sine of pi divided by 6. And the answer I got was a half. Now, the answer you just gave me is for the cosine. And let's do the cosine of pi divided by 6. You see, it's an ugly decimal. If you take the square root of 3 and you divide it by 2, do you see it's the same ugly decimal? There's only really 3 fractions you need to remember, apart from the obvious one like zeros and ones, which I'm not even counting as fractions, that you need to know. So for instance, the third one is root 2 over 2. And every single one of these guys here, exception of that one, right? They're special cases. These middle ones are the standard angles. What's the cosine going to be?
It's the same.
It's the same,
it's
right? Now, what is the sine of pi upon 3? Because there's a pattern here as well. So if you just remember the 3 guys, you can get all these guys. So what's the sine of pi upon 3?
This one is root 3 over 2.
Correct. And what does that make the cosine of pi upon 3?
1/2.
Agreed. Now, if you want to find the tangents, as long as you can remember these guys, you can get the tangent. You just have to do a bit of extra work and a little tidying up. So suppose I wanted to know the exact value of the tangent of pi upon 6. I'm going to use the identity that it's the sine of pi upon 6 divided by the cosine of pi upon 6. And the sine of pi upon 6 is a half, and the cosine of pi upon 6 is that. These always cancel out, and there is my answer. But we make it look pretty by rationalizing the denominator. And that's your answer. Root 3 over 3. Now, if you wanted to know the tangent of pi upon 4, you take this guy and divide it by that guy, and you get 1. If you want to know what the tangent of pi upon 3 is, you take the sine of pi upon 3 and you divide it by the cosine of pi upon 3. And the sine of pi upon 3 is that guy, and the cosine is that guy. The halves cancel, and you are left with the square root of 3. Now, if I wanted to find the secant of pi upon 6, find out what the cosine is and turn it upside down. If I wanted to know what the cotangent of pi upon 3 was, right? Wouldn't I find the tan and turn it upside down? So if you know all these 6, in fact, if you only know these 6, can't you get these 3? And then if you know all these 9, the reciprocals of them will be the secant, the cosecant, and the cotangent. Now, the other angles that I haven't covered are like, you know, pi upon 2 and 3/2 and pi's. Those you can plug into your calculator because you typically get 1s, 0s, or undefined. Right. So if you try to find the sine of pi or the sine of 1/2 pi or 3/2 pi, the answers tend to be 0, 1, or undefined, depending on which trig function. So it sounds to me like some of you at least need to refamiliarize yourself with these guys, because when you do equations of tangent lines, don't you have to know what the sine of pi upon 3 is, you know, as part of the calculation? And you're not allowed decimals, so it must be exact values, otherwise